Welcome to EPG Pathshala. I am Aparna, working as scientist, MFPI Food Quality Control Laboratory, Professor Jaishankar, Telangana State Agricultural University, Hyderabad. Today, we are going to learn about fat-soluble vitamins. In this topic, we will learn about the properties, the stability, the modes of degradation of all these fat-soluble vitamins, their importance in the diet, and the nutritional properties of all the fat-soluble vitamins. Vitamins, by their definition, are essential to health and they have to be obtained from the food which we consume on a regular basis, except for vitamin D, which is obtained only by exposing ourselves to sunlight. In terms of medicine and nutrition, our knowledge of vitamins is relatively recent. Although James Lind discovered an association between lime juice and scurvy in 1753, it was over 170 years later that vitamin C was eventually isolated. The understanding of vitamin B12 goes back to only 1950s, and new roles for folates were still being discovered in the late 1990s. Man's supply of vitamins is obtained from a variety of diet which consists of vegetables, cereals, fruits, meats, and different quantities of vitamins which are present in all the dietary components which we consume. Now, coming to the classification of vitamins and understanding vitamins, vitamins are heterogeneous groups of substances which are vital nutrients that must be obtained from the diet. Although a number of these were termed vitamins between 1930s and 1950s, nutritional science now recognizes only 13 substances or groups of substances as being true vitamins. The 13 substances are divided into two broad categories: the water-soluble vitamins and fat-soluble vitamins. Today, we will learn about fat-soluble vitamins. The fat-soluble vitamins are 4 vitamins. One is vitamin A, vitamin D, vitamin E, and vitamin K. We have water-soluble vitamins in which there are 9 vitamins, which are vitamin C, B1, B2, B6, B12, niacin, pantothenic acid, and biotin. Let us now understand the factors which affect the vitamin stability in the food systems. One of the very few attributes that the vitamins have in common is that none is completely stable in the foods. The stability of individual vitamin varies from relatively stable, such as in case of niacin, to relatively unstable, such as in case of vitamin B12. The factors that affect the stability vary from vitamin to vitamin, and the principal ones are to be discussed now. The deterioration of vitamins can take place naturally during the storage of vegetables, fruits, and foods, and because of losses which can occur during the processing and preparation of various kinds of foods, their ingredients, particularly when the foods are subjected to high temperatures. The factors that affect the degradation of vitamins are the same whether the vitamins are naturally occurring in the food or added as a part of fortification to the food. There are various kinds of factors which affect the stability of vitamins. The factors are temperatures, moisture, oxygen, light, pH, presence of metallic ions like copper, iron, etc., presence of other vitamins, then other components which are present in the food such as preserving agents like sulfur dioxide, etc., and a combination of all these factors which I have mentioned now. However, the form in which a synthetic source is used can enhance its stability. For example, vitamin E, that is the tocopherol esters, are more stable than the tocopherol form by itself. With the increased use of nutritional labeling of food products, vitamin levels in foods have become a very important subject of label claims that can be easily checked by the enforcement authorities. This poses a number of problems for the food technologies. When more than one vitamin is the subject of a quantitative label claim for a food, it is very unlikely that the vitamins will deteriorate at the same rate. If the amounts of these vitamins are included in nutritional labeling, the shelf life of the food is determined by the life of the most unstable component. In order to comply with the legal requirements of maintaining the label claim throughout the declared life of a food product, the food technologists need to obtain a reasonably accurate estimation of stability of each of the vitamin which is present in the product. This has to be evaluated in the context of food system, whether it is a liquid food or whether it is a solid food, the packaging, the probable and possible storage conditions which can be achieved by conducting well-organized research studies. Let us now move forward in understanding all the fat-soluble vitamins. Among the fat-soluble vitamins, the first one we have is vitamin A. Nutritionally, the human body can obtain its vitamin A requirements from two sources. One is from the animal sources, that is in the form of retinol, and the second way is to obtain vitamin A from plant sources in the form of beta-carotene and related carotenoids. Both sources provide a supply of vitamin A, but by different metabolic pathways. In terms of stability, the two sources are different from each other, first one being from plant source and second being from the animal source. Vitamin A is one of the more labile vitamins and retinol is less stable than the retinyl esters. The presence of double bonds in its structure makes it subject to isomerization, particularly in an aqueous medium at acid pH. The isomer with highest biological activity is the all-trans vitamin A. The predominant cis isomer is 13-cis or neovitamin A, which only has a biological activity of 75% of all the trans isomers, and 6-cis and 2,6-di-cis isomers, which may also form during isomerization, have less than 25% of the biological activity of all the trans form of vitamin A. The natural vitamin A sources usually contain about 1/3 of neovitamin A, while most synthetic sources generally contain considerably less. For aqueous products where isomerization is known to occur, mixtures of vitamin A palmitate isomers at the equilibrium ratio have been produced commercially. Vitamin A is relatively stable in alkaline solutions. Vitamin A is sensitive to atmospheric oxygen, with the alcohol form being less stable than the esterified form. The decomposition is catalyzed by the presence of trace minerals. As a consequence of its sensitivity to oxygen, vitamin A is normally available commercially as a preparation that includes an antioxidant and often a protective coating. While BHA, that is butylated hydroxyanisole, and BHT, that is butylated hydroxytoluene, are permitted in a number of countries for use as an antioxidant in vitamin A preparations, the recent trend has been towards the use of tocopherols, that is the use of vitamin E. Both retinol and its esters are inactivated by ultraviolet component of the light. In general, vitamin A is relatively stable during food processing involving heating, with palmitate ester more stable to the heat than the retinol. It is normally regarded as stable during milk processing, and the food composition tables give only small differences between the retinol contents of fresh milk, whole milk, sterilized milk, or any other processed milks like UHT and treated milks. However, prolonged holding of milk or butter at high temperatures can lead to a significant decrease in the vitamin A activity. A provitamin A is a compound that can be converted in the body to a vitamin, and there are a number of carotenoids with provitamin A activity. Carotenoids are generally found as naturally occurring plant pigments that give the characteristic yellow, orange and red colors to a wide variety of fruits as well as vegetables. Some can be found in the liver, kidney, spleen and milk also. The provitamin A with the greatest nutritional and commercial importance is beta-carotene. The stability of the carotenoids is similar to vitamin A in that they are sensitive to oxygen, light as well as acid media. It has been reported in some studies that treatment with sulfur dioxide reduces the carotenoid destruction in vegetables during dehydration as well as during the storage of fruits and vegetables. Some more research into the effect of sulfur dioxide treatments on the beta-carotene stability in dehydrated vegetables have been giving varying results, and it has been postulated that the effects of drying or dehydration and storage conditions on the stability of sulfur dioxide has a consequential effect on the stability of the beta-carotene present in the food matrices. Studies on the heat stability of both alpha-carotene and beta-carotene showed that beta-carotene was about 1.9 times more susceptible than alpha-carotene to heat damage than during the normal cooking and blanching processes. Products containing beta-carotene should be protected from light and headspace air to keep to the minimum. After understanding vitamin A, the changes in vitamin A, provitamin A and retinol during processing and storage, let us now move forward to the second fat-soluble vitamin, that is vitamin E. A number of naturally occurring substances exhibit vitamin E activity, including alpha, beta, gamma tocopherols and alpha tocotrienols. Dietary sources of vitamin E are found in a number of vegetables and cereals, with some vegetable oils such as wheat germ oil, sunflower seed oil, safflower seed oil, maize oils being particularly very good sources of vitamin E. Both synthetic and naturally sourced forms of vitamin E are available commercially. While the natural sources of tocopherols, which also have the highest biological activity, are in D form, the synthetic versions can only be produced in the DL form. Both the D and DL forms are also commercially available as esters or in the esterified forms. There is a considerable difference in the stability of tocopherols of vitamin E and the tocopherol esters. While vitamin E is regarded as being one of the more stable vitamins, the unesterified tocopherol is less stable due to the free phenolic hydroxyl groups. Vitamin E is unusual that it exhibits reduced stability at temperatures below freezing. The explanation given for this is that the peroxides formed during fat oxidation are degraded at higher temperatures but are stable at temperatures below 0 degrees centigrade, and as a consequence can react with vitamin E. It has been shown that alpha tocopherol may function as a pro-oxidant in the presence of metal ions such as iron. Alpha tocopherol is readily oxidized by air. It is stable to heat in the absence of air but is degraded if heated in presence of air, and is readily oxidized during the processing and storage of food matrices containing the alpha tocopherol. One of the most important naturally occurring sources of tocopherols are the vegetable oils, particularly the wheat germ oil and cottonseed oils. While deep frying of oils may result in loss of vitamin E up to around 10%, it has been found that storage of fried foods even at temperatures as low as minus 12 degrees centigrade can result in significant loss of vitamin E. After understanding vitamin A and vitamin E, let us now move forward and try to understand the next fat-soluble vitamins, that is vitamin D. Vitamin D is present in nature in several forms. Dietary vitamin D occurs predominantly in animal products with very little being obtained from plant sources. Vitamin D3 or cholecalciferol is derived in animals including man from the ultraviolet irradiation of 7-dehydrocholesterol which is present in the skin. Human requirements are obtained from both endogenous production in the skin and from dietary sources. Vitamin D2, it is also called as ergocalciferol. Vitamin D2 is produced by ultraviolet irradiation of ergosterol, which is widely distributed in plants and fungi. Both vitamins D2 and D3 are manufactured for commercial uses and for commercial applications. Both vitamins D2 and D3 are sensitive to light and can be destroyed relatively and rapidly if exposed to light. They are also adversely affected by acids. Preparation of vitamin D in edible oils are more stable than the crystalline forms, and the vitamin is normally provided for commercial usage as an oil preparation or stabilized powder containing an antioxidant. Usually the antioxidant can be tocopherol. The preparations are normally provided in light-proof containers with inert gas flushing. The presence of double bonds in the structure of both forms of vitamin D can make them susceptible to isomerization under certain conditions. Studies have shown that isomerization rates of ergocalciferol and cholecalciferol are almost equal. Isomerization in solutions of cholecalciferol, it resulted in an equilibrium being formed between the ergocalciferol and precalciferol, with the ratios of the isomers being temperature dependent. The isomerization of ergocalciferol also has been studied in powders which are prepared with calcium sulfate, calcium phosphate, talc and magnesium trisilicate. It was seen that isomerization was catalyzed by the surface acid of all these additives. Crystalline vitamin D2 is sensitive to atmospheric oxygen and will show signs of decomposition after a very few days of storage in presence of air at ambient temperatures. Crystalline cholecalciferol D3 is also destroyed by atmospheric oxygen but is relatively more stable when compared to vitamin D2, which could be due to the fact that it has one less double bond. The vitamin D3 naturally occurring in the foods like in milk, fish, etc., it is relatively stable to heat processing. So after understanding vitamin A, vitamin E and vitamin D, let us now move forward to the fourth fat-soluble vitamin, that is vitamin K. Vitamin K, it occurs in many forms. The most predominant are two forms. One is vitamin K1, which is also called as phytomenadione or phylloquinone. This vitamin K1, it is found in green plants and vegetables, potatoes, fruits, etc. Then we have the second most predominant form, that is vitamin K2. It is also called as menaquinone. And this vitamin K2 can be found in animal and microbial materials. The presence of double bonds in both vitamin K1 and vitamin K2 makes them liable to isomerization. Vitamin K1 has only one double bond in the side chain in the 3 position, whereas in K2 double bonds recur regularly in the side chain. Vitamin K1 exists in two forms, that is either transform or as cis isomer. The trans isomer is the naturally occurring form and is the one that is biologically active. The cis form has no significant biological activity. The various forms of vitamin K are relatively stable to heat and are retained after most cooking processes. The vitamin is destroyed by sunlight and is decomposed by alkalis. Vitamin K1 is only slowly decomposed by atmospheric oxygen. Vitamin K is rarely added to food products and the most common commercially available form is K1, that is phytomenadione, which is insoluble in water. A water-soluble vitamin K3 form is available and it is available as menadione sodium bisulfate. Now let us look at the vitamins lost during the processing. As we have already seen in the beginning of this chapter that all the vitamins exhibit a degree of instability, the rate of which is affected by a number of factors. Naturally occurring vitamins in foods are susceptible to many of these factors during harvesting, processing and storage of food and its ingredients. It is particularly important that the effects of processing are taken into consideration when assessing the vitamin stability in any kind of food matrix, as the food may have been subjected to a very high number of adverse processing techniques during the food processing. The most common factor during processing is application of high temperatures, which in some cases can be canning and it can be for a long period of time also. Most of the research which is done on stability of vitamins in fruits and vegetables during blanching and canning was carried out way back from 1940s to 1950s, and even now there is a lot of research which is going on. Although there have been refinements in both processing and analytical techniques, many of the conclusions drawn from the research is still valid. Let us now look at the various processing techniques where the vitamin's presence or stability can be disturbed. The first processing technique is blanching. In terms of blanching, it was found that a high temperature, short time water blanching gives better vitamin retention than low temperature and long time blanching, and that the overall steam blanching will be superior to the water blanching. The addition of sulfite to the blanching water also showed to affect significantly the thiamine levels which are present in the fruits and vegetables. Beta carotene was found to be the best survivor during the blanching of all the vitamins. Riboflavin had retention in the range of 80 to 95%, whereas vitamin C was in the range of 70 to 90% under optimum conditions, and niacin up to 75 to 90%. Now the second technique is heat processing. Studies on heat processing of fruits, vegetables and other food matrices in different kinds of packaging materials showed significant loss of vitamin C and thiamine. In some cases, the vitamin C levels assayed immediately after heat processing were between 15 and 45% of fresh product, and these values further reduced during the storage. Thiamine reduced by almost 50% during heat processing and further declined to between 15 and 40% to the original level after a year's storage. Riboflavin losses were found to be between 12 and 15% during processing, but levels of about 50% of the original were observed after 1 year of storage. Niacin was most stable with initial loss of 15 to 25%, but with much less than the riboflavin being lost during the storage. Beta carotene was found to be relatively stable. In milk, the fat-soluble vitamins A and D are relatively stable to the heat treatments used for processing of milk, as they are water-soluble vitamins, that is riboflavin, niacin, pantothenic acid and biotin. Vitamin C, thiamine, B6, B12 and folic acid were all affected by heat processing of milk. With more severe the process, the greater the loss. With the exception of vitamin C, vitamin losses are generally less than 10% after pasteurization of milk and between 10 to 20% after UHT, that is ultra high temperature treatment. Average losses following sterilization of milk are reported to be as high as 20% for thiamine, vitamin B6, B12 and 30% for folic acid. Research has shown that stability of vitamin C during processing of milk is also affected by the presence of oxygen during the processing. Average losses of vitamin C were 25% after pasteurization, 30% after UHT and 60% after sterilization. However, vitamin C appeared to be particularly well retained in condensed full cream milk than the ordinary milk. Then coming to B vitamin stability during the heat processing and cooking of meats, it was varying very widely. Cooking conditions had a marked effect on the stability and retention of thiamine in animal products like beef, pork, etc. during the roasting temperatures. The vitamin content of the drippings, if taken into consideration, it was found that riboflavin, niacin and B12 are stable during cooking of the meat. Pantothenic acid losses in cooked meat were between 10%, although very high losses of folate of over 50% has been found in the meat processing. Post-mortem aging of beef also resulted in the loss of 30% of niacin over 7 days period. Then baking products. In baking of bread, it was seen that 20% loss of thiamine was found, 17% loss of vitamin B6 was found, and up to 1/3 of natural folate content was lost during baking of the bread. Niacin and pantothenic acid were normally stable during the entire baking process. So after blanching and heat treatment and their effect on vitamins, let us now move forward to the next processing technique, that is freezing. Although most of the vitamins are stable in frozen fruits, vegetables and other food matrices for periods of up to almost 1 year, losses of vitamin C have been found to occur at temperatures as low as -23 degrees centigrade. Remaining all vitamins were intact during the freezing process. Then moving on to the next processing technique, that is dehydration. Research on dehydration of blanched vegetables and other food matrices showed that dehydration process resulted in additional losses of both fat-soluble and water-soluble vitamins. It was seen that dehydration of blanched cabbage, it has given an additional 30% reduction in vitamin C content also, apart from 5 to 15% niacin content loss and about 15% of thiamine loss. Then the next processing technique, that is irradiation, and effect of irradiation on the stability of vitamins in the food matrices. The use of ionized radiation as a sterilization technique for foods has been accepted in a number of countries legally also. In many countries, the foods and ingredients that are allowed to be irradiated are restricted by law, and the process is normally only used for foods at high risk or high levels of microbial contaminations. With the treatment of ionizing radiation or irradiation, it was seen that the vitamin content of the foods was significantly affected with the dosage of irradiation given to the food matrices. It was seen that at low doses, that is dosage around 1 kg, the loss of vitamins is not very significant. Whereas at high doses of irradiation, that is doses which are higher than 3 to 10 kg, it has shown that vitamin losses were significantly found. and that the foods that are exposed to air during irradiation and the subsequent storage was very high as compared to low irradiation doses. At highest permitted radiation doses, care has to be taken to protect the food by using suitable packaging material to exclude air and by carrying out the irradiation at a possible low temperature. There is evidence that fat-soluble vitamins like vitamin A, E and K and the water-soluble vitamins like thiamine are most sensitive to gamma radiation, whereas niacin, riboflavin and vitamin D are relatively stable. There is conflicting evidence for vitamins with some foods showing significant losses, whereas other foods not much of changes. If it is intended that nutrition claims are to be made for irradiated foods, it is essential that the studies are carried out on the content and stability of vitamins after the treatment with different doses of ionizing radiation. After understanding the effect of processing techniques on the vitamin losses, let us now learn about vitamins and their shelf life. As the tendency to include nutritional information on the labels of food products has increased, so have the liabilities of the manufacturers. For many, if not most, foods, the inclusion of nutrition information is optional, but any statement made on the label come under the force of law. A company making any inaccurate voluntary nutritional declaration can be subject to prosecution. Within a nutritional information statement, vitamins are the main category of declared nutrients where the quantities can significantly decrease during the shelf life of the food product also. The vitamin content of the processed foods can decrease all through the storage, and it has already been pointed out through research that losses of vitamin C can occur in frozen vegetables, fruits, etc., which are stored at -23 degrees centigrade. If declaration of vitamin levels are required on the label, whether voluntary or statutory, the manufacturer needs to carry out suitable trials to determine the stability of each vitamin which is claimed on the nutritional label and all through the shelf life of the product. The actual procedures used for the study should depend on the composition of the food, the processing procedure, and the form in which it is presented and stored. The type of packaging also can have a significant effect on the vitamin stability as well as the quality of the barriers to the oxygen, moisture and light in the packaging material is very important. A requirement for label claims for vitamins can influence the selection of the form of packaging. The need to retain the vitamins often means that a compromise has to be achieved between the length of required shelf life and the barrier properties of the packaging films. Due to wide variety of products, processing and packaging, it is not possible to give specific procedures for determination of shelf life of all the vitamins in the food. However, there are some guidelines which are established for determination as well as prediction of shelf life of the vitamins. The determination of vitamins at each stage of shelf life study should be made on a specific protocol. As the degradation of most of the vitamins follow first order or zero order kinetics, it is possible for shelf life predictions to be made using a classical Arrhenius model on the assumptions that models holds for all the reactions which are being studied. When it is possible to add vitamins to a food either to restore losses during processing or to fortify the food, it is a common practice to add an amount above the label claims to compensate for losses which can happen during the storage of the food product. This additional amount is called as overage and is normally quoted as percentage of the claimed level. For example, if a label claim is made for 60 mg per serving of vitamin C, it is determined that a 10% overage is required to achieve a stored shelf life for 1 year. The input of vitamin C would be 110% label claim, or 66 mg per serving will be added. The amount of overage should be reasonable and well within any safety concerns for the vitamin. It is very important to protect the vitamins which are present in the foods. For all products for which claims for vitamins are intended, it is essential that all stages of the processing, handling and storage of the product are evaluated to minimize the degradation of the vitamins. And this can be accomplished by keeping residence times at higher temperatures to a minimum and reducing or eliminating exposure to light as well as oxygen. For example, during the processing of fruit juices, fruit squashes, fruit drinks, meat products, etc., the deaeration of the solution can have a protective effect on the vitamin C levels, which are produced by reducing or eliminating the oxygen. In other words, latest research says that modified atmospheric packaging also can be utilized for retention of vitamins to a longer period of time. Commercial sources of vitamins for addition to foods can be obtained in forms that have been encapsulated or coated to improve their stability all through the storage life of the food products. So today we have learnt about fat-soluble vitamins, that is vitamin A, D, E, K, the factors which affect the stability of the vitamins, and more importantly about the sources of fat-soluble vitamins, their processing losses and what can be done during the processing. You can refer to books like Food Chemistry written by Nelson, Advanced Food Science for further information. Thank you.